So these are the slides for the Ramsey growth model. So the main difference between the Ramsey growth model and the solo growth model that we covered last session is that in the solo growth model, there's no real decisions. So, it's only kind of loosely an economics model in the sense that there's no consumers making decisions, no firms making decisions, etc. So in the Ramsey growth model, we're going to think about both of those things. Households making decisions about how much they want to work. Well, I should be a little bit careful here. In this version of the Ramsey growth model, we're going to assume that people provide 1 unit of labor, but certainly they're going to decide how much they want to consume versus how much they want to save. And firms are going to decide how much capital they want to use versus how much labor they want to use in production. And both households and firms are going to do that in order to optimize their utility in the case of households, and then profits in the case of firms. Okay, so this is going to be a very typical economics model, and we're going to be using this sort of thing again and again. Why is that important? Well, one reason why it's important is that, if economists want to give policy advice, why isn't that working? Mouse. If economists want to give policy advice, the solo growth model said, well, we should just choose the savings rate. Well, it's not so easy to choose the savings rate. In the real world, you don't do that. You can indirectly do it through choosing the interest rate. And that's kind of the message of this Ramsey model, is that the interest rate is going to be really critical in figuring out how much households actually save. So just repeating what I just said again, optimization in this model is going to be similar to what it is in the rest of the models we look at in this course, so that's good for you. Okay, another thing I didn't mention yet is that this is going to be a general equilibrium model in the sense that prices, so that's the price of output, the price of wages, and the price of capital, renting capital, is going to be determined in equilibrium. And you may have heard of DSGE models. So central banks these days use something, yellow is not a great color here, let's try blue. Central banks these days use DSGE models as one of their primary tools for predicting the effect of, say, monetary policy. Today, the model we're going to look at is going to be a DGE model. So it's a dynamic general equilibrium model. It's not going to be stochastic because there's not going to be any shocks, any uncertainty about the way that the world unfolds. People are going to be able to predict forward the path of wages, the path of the interest rate. So they'll be thinking about the future. The model's going to be dynamic, but they won't be surprised ever. Okay, so without further ado, let's get into the details of the model. So there's two types of decision makers, or agents, in this economy. Agents is a word that economists love to use to describe the actors in economics models. So the agents are households and firms. There's going to be a fixed number of households in the economy, but the number of workers in each household, or the number of consumers in each household, is going to be growing over time at an exogenous rate, n. So it's similar to the way we looked at things in the Ramsey model, in the solo growth model. If you think about it, there's sort of a tricky reason that we're going to assume that there's a certain number of households in the economy. Keep in mind that the number of households in the economy could be 1. You could just have one gigantic household, but there's a tricky reason why we're doing this, and I'm not sure if I'm going to mention it in class. I'll just mention it here because there's no reason to keep you in suspense. But we need to think about the way that we value the welfare of current versus future consumers. And one way to do that is just to be a utilitarian. Suppose we're a social planner and we treat the utility of everyone exactly the same. Another way to do it is to think about a household, and then parents care about their children a certain amount and children care about their grandchildren. So there's this natural sort of path of discounting that's involved in that way of aggregating utility. And that's why we're making this sort of a household decision. People care about the future, but they care about the present more. And that's even true in thinking about sort of later generations. So, it's an important philosophical issue to talk about. I'm gonna not talk about it right now, but I'll just mention very briefly that there's no real philosophical reason why we should be discounting the utility of future people. We do it in every economics model because it helps us to solve these models. Otherwise, maybe you want to save a lot in the present and then reap the returns in the future. This idea of impatience would be important for us. You'll see where it comes in the model. I'll point it out when we get there. But just generally, there's not really a good philosophical reason that we should be discounting the utility of future people relative to present people. But we do it anyway, and you'll see where it comes, and you'll see why it's important in these models. So that's the trick. I'm not sure if I was coherent there. It doesn't really matter that much. For now, let's just take it as an assumption. So this is an important thing as well. So we're going to assume that every member of the household is going to be supplying 1 unit of labor. In particular, the amount of labor that's supplied is not affected by the wage. Everybody works full time, and doesn't matter what the wage is. You work full time. Period. Okay. Next one. Households are going to own capital, but there's not going to be any depreciation. So in the solo growth model we looked at, you recall that we had a delta that we interpreted as the depreciation rate of capital. We're just going to abstract from that in this model. It's not really important that we abstract from that. I think it's just that there's a lot of things floating around in the model, and it's easier just to consider one less sort of thing in the model. Putting it in isn't going to change any of the results in any sort of important way. It's just going to make it easier for us to exposit the model. Okay, firms are going to produce, they're going to use capital and labor, and they're going to choose how much of each one optimally given the prices, the wage, and the rental rate of capital. And finally, we're going to assume that markets are competitive in the sense that every firm and every household is going to consider itself to be very small, so that it has to take the prices as given. There's no market power. So firms can't produce a little less to raise the price in order to get higher profits, and households also can't supply labor a little less than they can't supply a little bit less labor to raise the price of wages, or supply a little bit less capital to increase the price of rental rate of capital in order to maximize their budget. Now, I'm going to be using two terms here somewhat loosely. Sometimes I say rental rate of capital, and sometimes I'll say rate of return. These two concepts are somewhat different, but in this model they're actually going to be the same because we're in continuous time. So the rental rate is sort of what a firm has to pay to use my capital right now, and then the rate of return is going to be what I can sort of expect the additional, I have to be a little bit careful in my language here, the additional capital, say, that I can receive by holding onto my capital today and selling it tomorrow. So you can see that these two things are in principle distinct, but when we're looking at continuous time, then since one moment is just no time at all, they're actually going to kind of collapse to be the same thing. So I'm going to be referring to them sort of as in the same way as R or R of t. But in principle they're distinct. It's just that when we're working in continuous time, they're actually going to be the same. Okay, so having said that, let's first focus on households before we turn to firms. So household utility, we're going to assume that it can be written like this. So how do you read this? Well, we have a certain amount of labor in the economy. So LT is the total amount of labor in the economy at time t. So LT, total labor in economy at t. Okay. And then we have H households, all of equal size. So we can just divide the total amount of labor in the economy by the total number of households to get the amount of labor, or the amount of workers, if you like, in the household. All right. Now, here, this utility here is going to be utility for each person in the household, each consumer or laborer in the household. And C then, we're going to interpret C of T as the amount of consumption per worker in the household. Okay, so C of T is consumption per worker. L of T is the total amount of labor in the economy at time T. Right, and then this little U is the amount of utility per worker. And the argument again is the consumption per worker. Right, how does the household aggregate up this utility? Well, at any given time, at any point in time, this is like the instantaneous utility of the household. The number of household members times the utility per member, right? And then we're looking at this this utility going from time 0 to infinity, and the household's going to discount this utility with rate rho. So what this says is, the higher is rho, the less households care about future generations or future times. I think I said everything I need to say about this slide. Is there another bullet point? Oops. I got my mouse set to page down on the scroll wheel, which is somewhat annoying. I should change that. So that's population growth rate N. I think I mentioned that in the last slide. Yeah, I think I mentioned everything here. Testing. Turn this volume down a little bit. This music's getting very loud. The worst thing would be if I had to re-record this because the music was too loud. So let's scale that down a bit. Okay, this slide is identical to the one we had in the solar growth model slide, so I'll hardly even say anything about it, but we're going to assume constant returns to scale, which means we don't really care about the size of firms. They're all going to be zero profit and equilibrium. Okay, so the production function we're going to assume can be written in this intensive form way. I guess that falls out of the constant returns to scale assumption. And finally, we're going to assume that the production function satisfies the E-naughta conditions, which we discussed last time, so I will not rediscuss them here. So now let's think about the household's budget constraint. We talked about the household's utility given consumption. Now let's think about how much consumption the household can buy given the prices of labor and the rate of return on capital. Okay. So how do we want to think about that? We're going to think about the budget constraint at time 0. So only one budget constraint. There's no uncertainty in this model, so actually the household can sort of plan all future consumption and investments, can plan it all at time 0. There's no surprises. This is just a dynamic general equilibrium model, not a dynamic stochastic general equilibrium model. Okay. So this is hardly a trick, but I say it's a trick here. Why did it do that? It's interesting. Okay. Well, anyway, so this rental rate of capital or the rate of return of capital isn't necessarily going to be constant. It's going to depend on the amount of capital we have in the economy. In steady state, we're going to assume it's constant, or derive that it's constant. But, I mean, the reason why is because there's going to be sort of a fixed amount of capital per unit of effective labor, just as in the solar growth model in steady state. But, you know, generally off of steady state, this rate of return on capital can be very different as you know, the capital per unit of effective labor grows or falls. All right. So, that mouse wheel. So as the interest rate changes over time, we want to think about how does a unit of investment at time 0, how do we change that into return at time t? Well, it's going to depend on this whole integral. So let's see if we can talk about how to write that out. So let's see here. I'm just going to pause the video for a second so that I don't confuse you while I think about how to do it myself. And I'm also going to get a drink of water. Okay, I'm back. I am hydrated and I worked out how to do this. So what I want you to do, let's see if I get myself a little more room here. Oops, over here. All right, so what does it mean to have an investment at time 0 and get return? How much return do we get by time? Well, let's just say, how does investment change at time t? Well, it's going to be the rate of return, the instantaneous rate of return, times the amount of investment that we have at time t, right? So what we can do is we can actually just divide both sides here by I. And I'll erase this guy. Oh, it's got a text. All right, so now we have this nice equation. Now let's integrate both sides, and what we're going to get is the integral of it dt divided by it is actually just log of it. And then the other side is going to be integral from 0 to t. I should be careful here. We're integrating, it's a definite integral going from 0 to t. So we got to give it a big T here. And it's going to be our little t dt plus a constant. Okay, and if you plug in 0, you're going to see that this constant is just going to be log of it's actually just going to be log of I at time 0. Okay, now notice this is actually just our definition of big RT. So I could just write here, I can take the exponent to both sides and get that I at time big T is going to be equal to I at time 0 times e to the power big R T. Okay. So that derives our equation here. 1 unit of investment at time 0, so if I of 0 is equal to 1, it's going to yield e to the power big RT at time big T. All right. So if this investment rate is constant, then that means that this here is not r of t, it's just little r. Well, then if we integrate from 0 to t, we're just going to get little r times t, big T in this case. So that's where that big R comes from. That's how you get that expression that a rate of return, or the return on an investment of 1 at time 0 is equal to e to the power rt. It's from this, this derivation. Hold on 1 second, just have to reply to a text. Okie doke. All right, so using that result, we can write out the household's budget constraint. Remember, we're asking, we're setting the value of all of the consumption for the household's entire lifetime from 0 to infinity equal to all of the household's income from 0 to infinity on the right-hand side. And there's some important things to note about this equation. We've written it out here. So here is the value of all of the household's consumption from now until forever. So these I could be putting a 0 here and an infinity here on all of these integrals. All right. Some things to note. Okay, so the first thing is there's no rows here. Remember, row is the discount rate of the household. That doesn't appear here. Why doesn't it appear here? It's because this is only about value. Okay, it's the value of all of this consumption from now to infinity, and then the value of all of the income from now to infinity, all discounted back to time 0 by this interest rate, okay, by this rate of return, if you like. Okay, so what else to mention? So what does the household have to start with? Well, it's got whatever capital it starts with. and then it's got all of its labor income. Okay, discounted now because labor in the future is worth less than labor now. And then what's it spending? Well, it's spending on consumption. So the value of its consumption is also written out here. Now just going into these various little bits, you'll recall that this is consumption per person in the household. So here is the number of people in the household at time t. All right, this is the income from wages. So this is going to be the wage per person. And this is the number of people in the household at time t. And I think that's pretty much all I have to say about that part. To use this, just as in the solar growth model, we want to put everything in terms of human capital, okay? Because we're going to have this growth rate of, the growth rate of capital is actually going to be positive forever. We want to set something equal to 0 in our steady state, and that thing we're going to set equal to 0 is just like in the solar growth model. It's going to be capital, physical capital per unit of effective labor. To do that, we want to put everything in terms of this physical capital per unit of effective labor, or per unit of human capital. Okay, so how do we do that? Well, we're going to divide everything by either ATLT, so the level of human capital, as in this case, or we've already got an LT here. We're just going to divide big C by AT, and then this is going to be consumption per unit of technology, if you like. So I'll just define it up here. So here CT is equal to consumption. Well, big CT is consumption per worker. Little CT is going to be consumption per unit of human capital. So it's going to be big CT divided by AT. Big CT is consumption per worker. Little CT is consumption per unit of human capital. Okay, so we're gonna, you can see that, we can write it this way, or we can write AT times little CT is equal to big CT. So that's what we're doing here, is we're replacing big CT with little CT times AT. On this side, we're replacing, I'll just write it over here again. Little KT is going to be equal to big KT. I should erase this thing so it's not confusing. Big KT divided by ATLT. Right. And then here we got this little WT. Big WT is the wage per worker. So we want the wage per unit of human capital. So again, we're going to have big WT times AT is equal to little WT, just like CT. Okay. And now things are looking better because we've got it all in, everything is in terms of consumption per unit of human capital, physical capital per unit of human capital, and now wages per unit of human capital. Okay. We can go one step farther if we want to get rid of the these ATLTs. Those are somewhat complicated. Let's take those out. We can do that by rewriting ATLT equals A0L0 times e to the power g plus nt. We derived that for the solar growth model, so I'm not going to derive it again. But you can just replace that here, and then you can replace it again here. All right. And now this is nice because you can see that these zeros and the A0, L0, H, these things don't depend upon time. So let's take those and pull them out on the next slide. So here's the final budget constraint. Am I good? Yeah, I should be. Is there another line here where I said this? Yeah, there was one more line. Okay, so what we can do here is we can actually just divide both sides of the equation by A0, L0 divided by H. So these guys are going to cancel. Okay. These guys are going to cancel, and these guys are going to cancel. Okay. It's just a constant. And that leads us to the next slide. If you just do that, then you're going to get this equation, which is our budget constraint, which is written in terms of everything per unit of human capital. So now we've got the utility function of the household. We've got the budget constraint of the household. We're also going to have one more condition here, what's called the no-Ponzi condition. And I want to talk about this, but I'm just going to take a quick break. Okay, sorry about that. So anyway, so what you can do here, I mean, it's written this way. It also makes sense this way, but let's actually just write this like this. Limit s to infinity, e to the negative rs. Ks has to be greater than or equal to 0. So what this is really saying is, notice what we're saying is when time approaches infinity, something here, so this is e to a negative positive power, here's the rate of return on investment, times k, which is like the amount of capital you have at time s, has to be greater than or equal to 0. So, you know, this thing, as time goes by, this is getting very close, this term is getting very close to 0, and this is like your capital holdings, which could be positive or could be negative, right? You could be borrowing in this case. So, so what this is basically saying is you can't just be borrowing so much that this term that's going close to 0 isn't going to sort of kill off your borrowing. So you can't, you know, just to say it in words, what's this thing capturing? It's capturing the idea that you can't just keep borrowing more and more and more money and then paying off your debt by borrowing more money, which in principle might be able to work if someone would lend you because, you know, I have an infinite stream of income into the future. So this is preventing people from doing this because if they could do this, they could arbitrarily increase their consumption to any level simply by borrowing against the future and borrowing more and more to pay off their debt in every period. You know, if they do that, then this thing is gonna explode, or at least end up being negative permanently as the negative capital holdings keep increasing and increasing and increasing, even as this thing is getting smaller and smaller and smaller. So yeah, we're ruling that out because we want people to actually expect that they're going to have to pay back their debt at some point in the future. Now, I say do we impose or we derive it? We kind of impose it, I think, is more accurate because this R here, this is an equilibrium object. And this K here is also, I can't read that yellow, let's do an orange, also an equilibrium object. So we're just saying that there's going to be some set of equilibria where people are just massively borrowing against the future. We're not going to allow that. We're going to say you have to expect to eventually pay back your debt and then get rid of all those equilibria. It's a very technical assumption. You're not even really going to see it in the rest of the derivations. It's just something that is sort of implicitly there in the background. Okay. To rule out that sort of equilibrium. All right, so that's kind of as far as we can go without getting more specific about exactly what sort of utility function we're going to look at. So from now on, and for many of the models in this class, we're going to be looking at this particular utility function, which is known as the constant relative risk aversion utility function. I'm not going to explain why that's true, but it just looks like this. Okay, and this theta here, I believe it's restricted to be greater than 0. But we'll see. Yeah, here it is, strictly positive. Okay, so we do restrict it to be greater than 0. All right, so we have a special case when theta is equal to 1. Although you can't see it from this equation, it actually is equivalent. You know, this is one of these things we're dividing by 0, right? So as theta gets very, very close to 1, the denominator here gets very, very close to 0. But then as theta gets close to 1 here, then we're taking, you know, if we're approaching from the left, we're taking increasingly more fractional powers of consumption, so it's getting more and more curved as we increase theta. So it's not exactly, of course, when you divide by 0, it's not exactly clear what's going to happen In this case, we're going to end up with log C of t in the limit. Okay, we have already made the budget constraint. We've put it in terms of everything per unit of human capital. Now let's put the utility function in terms of utility per unit of, it's gotta be a little bit careful here, right? It's actually gonna be per unit of technology. Did I say that here? Because this is the consumption of each person. So, yeah. So in other words, we want to put this in terms of CT divided by AT, big CT. Big CT divided by AT is what is the goal here. Okay, equals little CT. So anyway, let's look at the argument of the utility function. Or no, excuse me, the utility function itself looks like that. Now we can just, by this definition here, we can replace big CT with AT times little CT. Done it here. We know how AT grows. AT is equal to A0 times e to the power GT. So we'll just replace AT with that thing there. And then finally, we're just going to pull everything out and put it on the side. We're going to have A0 to the power 1 minus theta, e to the power GT times 1 minus theta, and then we're going to have this little CT over there. And that's kind of it. Now we want to think about the entire household utility. So of course we're discounting. Here's our big CT times the number of household members. Okay. So let's use substitute in our derivation of utility in terms of little CT here. So we're replacing this with that from the last slide. And then we're doing one more substitution. We know that LT is equal to L of 0 times e to the nt. We're assuming that the labor force, or the number of people in the economy, is growing with rate n. We get that here. Okay. Then let's take the things that don't depend on t and put them out on the left. So we're going to remove this a of 0. We're going to remove this L of 0 divided by h. Put them over here. And we end up with this expression. Let's just call this whole thing here b. And then over here, we're going to call, let's see here, rho minus 1 minus theta g minus n. We're going to call this thing beta. So we're just taking these three terms here and combining them into this little term. And now we end up with a very nice looking lifetime utility function that isn't too complicated and incorporates everything we've said so far. In particular, it's put in terms of consumption per unit for technology, unit of technology, I guess you'd say here. No, actually, I think it's right. We can say consumption per unit of human capital, right? So here's the number of household members. Here's consumption per household member. So this is already, big C already is consumption per person. Now we're dividing by A, so it's going to be consumption per unit of human capital. Let's not get confused there. I think I've been somewhat confusing talking about it, but hopefully that was clear. All right, so now we have the budget constraint in terms of everything per unit of human capital. We have the utility function in terms of everything per unit of human capital. We actually can already sort of solve the optimization problem then of the household. It's just going to be to maximize consumption per unit of human capital subject to the budget constraint. Okay. So that's what we're going to do first. And then we're going to sort of put workers and firms together and find an equilibrium. Oh, but first we're going to talk about the firm's maximization problem. Recall that these firms, they're going to use capital and human capital, physical capital and human capital, in order to produce. You can see that there's a little hidden assumption here. The price of output, we're going to assume that's equal to 1. We're not losing any generality there because you always need to have a numeraire. So we're just assuming the numeraire in this economy is just goods at any time t. Okay. So suppose that this economy produces apples. everything is going to be measured in terms of apples. So wages in terms of apples, rental rate in terms of capital of apples. So that's all. It's just a normalization assumption. We could put it in here; it wouldn't change anything. Okay, so let's look at first order conditions for the firm. Looks kind of boring here, but all we're saying is just that the firm is going to be taking the derivative of this production function with respect to labor minus the wage is going to give it, we set this equal to 0 to get the optimization condition, and then the same for the optimal level of capital that the firm wants to rent. All right, let's rewrite this thing in terms of little f rather than big F. So we just said that this is just saying that capital is paid its marginal product. Okay, so let's put that in terms of little f. So you'll recall that we can rewrite big F in its intensive form this way. So we can multiply by AL divided by AL, and that's going to be equal to AL little f of K divided by AL. Okay. Now let's take the derivative with respect to big K. Okay, so you can see that there's no big K here, so we don't have to worry about it. There is a big K there. We're going to use the product rule. The chain rule, and take the derivative here of the function, and then take the derivative of the argument of the function with respect to big K. And what does that give us? Well, you can see we have an AL here that cancels with this AL there, and we end up with f prime of little k. Let's do the same thing for the wage. Very similar idea, slightly more complicated. Why is that? Because we're taking the derivative with respect to L, and L appears here in this outside the little f function here. So we're going to take the derivative with respect to L, end up with this, a times f of k, f of little k. And then here, since we're again going to have f prime of little k, same as last time, but now when we take the derivative of the inside of the function, then it's going to look a little different. There's going to be a negative, and then we're going to have we're going to end up with an a up here, which cancels with the squared a in the denominator, so we only have a single unsquared a in the denominator when we're done. Okay, so one of these, this is going to cancel out. We're going to pull that a outside. We're going to get a times f of k minus, now here we have a big K divided by a and a single L, so that's little k times f prime of k. So this wage per unit of human capital is going to be little f of k minus k times f prime of k. All right, so now I'm going to tell you this, this looks a little bit complicated, but let me just informally say what this says. What is the return to workers? It's going to be total production minus the return to capital times the amount of capital used in production. That's slightly informal because this is all written in terms of things per unit of human capital, but that's how you can understand this equation. All right, so that's kind of all we need to solve the household's, well, that was the firm's problem. So we're done now with the firm's problem. So those, let me just flip back one slide here to say that while we're looking at it. So these things, R is equal to f prime of little k, so with this intensive form, and then also the wages are equal to these things having to do with the production function. These are results of the firm's optimization problem. Okay, so given little w or given R, firm is going to choose the amount of capital it employs per unit of human capital in order to satisfy these equations. Okay, so these come out of the firm's problem. Now let's talk about the households problem. So the household problem looks like this: maximize utility, subject to this budget constraint. Remember, households are going to take the wages and the initial capital endowment is given. Okay. And all they have to decide is how much do they consume. One other thing I want to mention about this budget constraint is there's only one of them. Okay, so this is the household's budget constraint sort of at time 0 looking forward. But since there's no sort of uncertainty or no stochastic shocks, the household can optimally plan its whole path of consumption perfectly. So there's no reason that we need to write a period by period budget constraint. We can just write everything at time 0 and then let the household plan optimally. Same is true here for utility. Since there's no uncertainty, the household's just going to plan its whole stream of consumption optimally. And that's important here because when we're going to look at this Lagrangian, we're going to optimize using the method of Lagrangian multipliers. When we do this, we want to be slightly careful because this lambda here is not going to have a time subscript. Why is that? Because there's only a single budget constraint. There's only a single lambda. Okay. So anyway, I think you guys have all seen a Lagrangian before. So what we do is we put in the thing we want to optimize. So this is the objective function. And then we add lambda times the budget constraint, basically. So this is just the budget constraint, and then we subtract off one side of it. Sometimes I talk about this in class, maybe we'll have a chance to say it, but if you think about the way that this sort of method of constrained optimization works, suppose we have a hill here that we want to optimize. So we want to find the highest points on this hill, but we want to find the highest point not unconstrained, we want to find the highest point along this line. Okay, so what this says is, this is like, this part of the objective function is the part that corresponds to the hill. Okay, so we want to maximize this thing, but we can't just find the unconstrained maximization. We want to find the maximization or the point along this line that leads to the highest utility. And you know, how does this work? Well, along this line and only along this line is this budget constraint going to be binding. So it says that these two terms minus this term is 0. Okay, so this is like our penalty. I should be a little bit careful here. It's actually slightly more intuitive to write this with a negative sign here. But you can imagine that here, this is C, this is the thing that we're trying to increase, right, in order to make this thing bigger. So this comes in with a negative sign. So the larger is C, you know, the lower is, the harder it is to raise, things. This is why it's good that actually I go through these before class. I think actually in class what I'm going to do is I'm going to take this minus sign, I'm going to change this slide afterwards. Take this minus sign, make this a minus, and then replace that with this, and then you can see it more clearly. What this is saying is only, you know, this is like a penalty. This term here is a penalty, and it's equal to 0 only along this yellow line. So we're always going to want to ultimately be finding a solution along this yellow line. Okay, so the highest possible points, like there, maybe. But anyway, that's just intuition for the Lagrangian. How this Lagrangian optimization works, it's not really important. If you know the algorithm, the technique, that's enough. So here it is. You got this Lagrangian function. You need to optimize this thing with respect to C of t. Of course, you know, C of t is a function of t, so you have to optimize it with respect to every single little t. So how do you write out the first order conditions? They look like this. Okay, so if you look, it's just going to be the inside of this thing. And there's not much else to say. And then the same thing here. only this one remains, right? Because there's only a C of t here. The reason why it doesn't really matter if this is negative or positive is simply because, you know, it's just about your interpretation of what lambda means. Okay, but anyway, that's what we get for first order conditions. All right, so let's take logs. Take the log of both sides. I mean, not too much to say about that. That's what you do, and you get this expression. This should hold. So in equilibrium, this has to hold at all times t, which means that we can actually take the derivative of both sides of that solution. And you'll see if we take the derivative, we're going to end up with negative beta minus theta times, well, the derivative of log c dot t divided by ct. And that's going to be equal to, notice that this guy is going to drop out. There's no t on the lambda, so lambda goes away. And then we have here, if we take the derivative of this expression with respect to t, I don't know if you guys know the rule, but that just means we're going to plug t into the integral and into the integrands and end up with that. Plus, here's just 1t plus n plus g. Okay, so here's this nice expression we get, which relates growth of consumption to these things that we care about, these other parameters of the model, I should say. In particular, growth of consumption is going to be related to the interest rate. Okay, so here's what we did. We took the derivative of both sides with respect to t. This is just copied from the last slide. Now let's solve for consumption growth. That's c dot t divided by ct. You get this expression. That's nice. And then finally, we're going to simplify one step farther. Recall that we actually defined what beta was a few slides ago when we were deriving the utility function that involved consumption per unit of human capital. We defined what beta was. Let's plug in that definition, and we end up with this guy here, which is nice because these are all now fundamentals of the model. Okay, so we can say that consumption growth, it's related to the rate of return on investment. It's related to discount negatively, and then it's related to growth of technology negatively, and also this parameter theta. Okay, so first let's talk about, which by the way is always greater than 0. Okay, so I mean, these are all sort of intuitive. I don't know if I talk about them on the next slide, so let me quick click through and see if I do. Yeah, I do actually say it here, but let me just mention it here first. So what this says is that if the rate of return on capital is higher, then we're going to raise our consumption more, which makes sense. Okay, so you know, if we get a better return on capital, then of course we're gonna be increasing the slope of our consumption, increasing our consumption as well. If we're more impatient, if rho is bigger, then our consumption is going to grow less because we're going to consume more today relative to tomorrow. So that part makes sense as well. And then finally, there's this term. If technology is growing faster, you know, if education is growing faster, say, than per worker, then we're going to actually have a slower growth of consumption. That makes sense because recall that this is consumption per unit of human capital, not per unit, not per worker. Okay, so you know, all else equal, if the sort of technology is growing faster, then consumption per unit of human capital is going to grow slower. Right, so that's the intuition here. Now we can write out one more thing. We can think about this consumption. We can think about consumption per unit of human capital. That's somewhat counterintuitive. Maybe it's easier to think about consumption per worker, which is what we actually care about. So recall that we have this nice relationship that C of t is equal to AT times little c of t. All right, so C dot of t is going to be equal to A dot of t times C of t plus A of t times C dot of t. okay? And then we can actually divide, actually let me be careful here. Divide both sides by C of t. Remember the definition of C of t is just A of t times little c of t. That guy gets cancelled out. Divide by A of t times c of t, little c of t. This guy gets cancelled out. So we end up with g plus c dot of t divided by c of t. All right, so that's how we get this expression. And we can just plug in our c dot, little c dot divided by little c. That's this expression, plus g. Okay. Now this this g here is going to cancel. So we can get rid of our g's. And you see that now all that matters is just, oh, I should be careful. This theta still remains over here, but of course, you see how it works with the algebra. I should be a little bit careful. Let's write it this way. Okay, and yeah, so we end up with this expression. And you know, this is maybe even more intuitive because when we think about consumption per laborer, then we don't have to have this counterintuitive thing that the faster technology is growing, the lower is consumption growth. It's just, you know, since every worker is more educated, they each get a little bit more consumption. So what matters at the end of the day? All that matters for consumption growth, whether it's positive or negative and how big it is, are three parameters or three quantities. They're not exactly parameters because this one's an equilibrium object, but these two are parameters. So what this says is if the rate of return on capital is bigger than the discount rate, then consumption will be growing. If it's less, the consumption will be shrinking. Okay, and that's all mediated by theta, which says sort of, which is exactly related to the intertemporal elasticity of substitution, which I realize we didn't talk about, but maybe we should. So all this, you know, so 1 divided by theta is something we call the elasticity of intertemporal substitution. So the bigger is this term, the more consumption growth reacts to changes in the interest rate. The smaller is this term, the less consumption growth reacts to changes in the interest rate. Okay, so that's why it's called the elasticity of intertemporal substitution. That's all there is to say about that. Yeah, okay. Okay, so we started with wages, but where did that go? Isn't that weird? All that we see here is the rental rate of capital. Okay, the reason why is because we sort of solve for wages in a sense, because it's all part of the individual's, well, let's put it this way. Wages are sort of given from the individual's point of view. They take wages as given, right? They see the path of wages, and since the household knows that it's going to work full time, remember we assume that there's no sort of decision from the household about how much to work. It means that the wages sort of are independent of the household's problem. And this expression is all about the household's problem. There's nothing about firms here in this expression. So the household doesn't react to, it takes the wages as given, okay? But the household does react to changes in the rental rate of capital because it's deciding how much to consume and how much to save, okay? So the household sort of, I don't want to say it's not sensitive to changes in the wage, it's just that it takes wages as given. Whereas it doesn't take the amount of capital stock is given. It internalizes that because it's part of this decision whether to save or to consume. So what's the difference between labor and capital? Capital is something that the household is accumulating over time, whereas labor in this case, for the household, from the household's point of view, I mean, it's use it or lose it always. So I mean, you can't save labor, you can't work a little bit less today and then work a little bit more tomorrow. I mean, you can to a degree, but there's a limit on how much you can do, right? I mean, I can't save up my labor for for an entire year and then just work, the extra labor the next year. You can't save it, right? I mean, it's either you work or you don't. That's kind of what I mean to say. Whereas with capital, you can sort of build it up. So that's kind of what I was trying to get at with these slides. Sort of a philosophical thing about how you can't save time. Time passes. You have to use it. You can't save it up and use it tomorrow. Okay, so anyway, now we've got the growth of consumption given the path of the rental rate of capital, path of rate of return. But this isn't quite equilibrium yet because we don't know how that rental rate relates to the stock of capital. Okay, but wait a second, we do. So let's move now from micro, where the firm and the worker both take the prices as given, and think about macro, where we're going to combine sort of the firm and the worker's problems. And here it is, right? So remember, the worker, they take the rental rate of capital as given. So their problem looks like this. Whereas the firm also takes the rental rate of capital as given, and they hire physical capital per unit of human capital in order to maximize their profits with this relationship. Okay, so all we're doing is we're just combining these two relationships into this guy. And why is this thing nice for us? Because it's going to relate the stock of physical capital per unit of human capital to consumption growth. And that's going to be our sort of, that's going to be one of the things we put on our graph where we're going to try to find a steady state. So our steady state, this little c dot t is going to be constant, and k dot t is also going to be constant. Okay. So where is c dot t constant? Let's look at this graph. So down here we have little k, over here we have little c, and right here we have c dot is equal to 0. So let's write this thing out so we can recall what this equation looks like. I'm taking off all the t's just to make things cleaner and easier to read. Okay, so note that there's going to be some level of little k here, where little k is exactly equal to rho plus g times theta, and that's going to be this k star here, this line where c dot is equal to 0. Okay, and then on these two sides, when little k is very high, since you guys will recall that this f of k is concave, right? So it looks like this. Right, so the slope is getting lower. So when little k is big, the slope of this thing is small, which means this whole numerator here is negative. So little c is decreasing on this side of this equilibrium line, and it's increasing on this side. Why is that? When little k is small, then this curve is steep, which means that this numerator here is positive, which means the capital stock is growing. Okay, so that is the first graph. All right, now we're going to have another equation we haven't even talked about, but we can get it just like we did in the solar growth model. So the change in the capital stock, it's going to be equal to savings minus break-even investment. Break-even investment, so previously we wrote this, I'll just write solo here. We had little k of t dot is equal to s f of k minus n plus g plus delta times little k. You guys recall this equation? Well, here we've taken away delta just to have one less thing to talk about, although adding depreciation of capital wouldn't change anything. So now we only have n plus g. And then savings here, it's not just going to be a fixed fraction of output. It's going to be a household's decision, which is total amount of output per unit of human capital minus consumption per unit of human capital. So otherwise, this is exactly the same equation. So let's do it. Let's put it on our graph. Again, hard to see if you don't rewrite it, so I'm going to rewrite it here so we can look at it at the same time. K dot is equal to f of k minus consumption minus n plus g times little k. Okay, so how does this work? Let's take a look at this thing. Let's actually solve here for where this is 0. So when little k dot is 0, then we have let's do it this way. I wish I went to put this t here. Let me get rid of that. I took all the other t's off, but I left one of them in. All right, we're gonna have c is equal to, when k dot is 0, c is equal to f k minus n plus g. Okay, so that's this line here, this k dot equals 0 line. All right, so how do we want to interpret this? Well, this n plus g times little k, that's increasing linearly. This f of k, you guys remember the production function again looks like this. It's very steep at the beginning, and then eventually it gets flat. Okay, so it's little k, this is f of k. Okay, so eventually this thing is flatter than this line with slope n plus g, which means that this curve is actually going to be going down. Okay, and in fact, eventually, at some level of little k, this is going to be equal to 0 consumption. That's this point right here. On the other hand, when we start out here, when little k is very small, oh my gosh, just realized you guys can't see anything here. Oops, let me move my little capture device over to here for now. Okay, so right, so this is about this line here, which is for k dot equals 0. Then we have this relationship, and what I was saying was this production function starts out very steep. Okay, so at first this thing is growing. This for small amounts of little k, this part is growing faster than that part, so that means this is increasing. Then eventually it gets to be the point where the slope of that is equal to the slope of that, which, by the way, what is that? What does it mean when the slope of the production function is equal to the slope of break-even capital line? It should be right here where the slope is 0. That is our golden rule consumption, but we'll talk about that in a minute. Okay, so that's where we get this line. At first, for little values of little k, this thing's growing, but then as little k gets bigger, eventually this thing starts decreasing, and eventually we can find a little k where this is equal to 0. Okay, so far so good. This is where k dot is 0. But now how do we figure out that k dot is decreasing up here, or little k is decreasing up here and increasing down here? Well, let's think about this. If c is very, very large, conditional on these two things, so let's just fix the level of little k, and then imagine a little c that's very big. Well, since we got a negative here, that means k dot is going to be less than 0, which means this thing's going to be decreasing. All right, now again, let's fix a little k, and imagine a very small c. Since there's a negative there, when c is very small, then k dot's going to be positive, which means little k is going to be increasing. Okay. So that is that. Now let's finally combine the two graphs. Okay. So along this line, let me move my face back to the other side again. Oops. Okay. Just can't see this it says K star on the bottom there. I can't keep both K star and C in. This is C over here. Okay, so we're combining these two lines. This is where K dot is equal to 0, like we just talked about, and this is where C dot is equal to 0. Recall that on this side of the C dot equals 0 line, we have a falling level of consumption per unit of human capital. On this side, we have a rising consumption per unit of human capital. Okay, so we can actually sign each of these quadrants. Okay, so in this area, capital is falling and consumption is falling. In this area, capital is falling and consumption is rising. In this area, capital is falling and consumption is falling. And in this area, capital is rising and consumption is rising. Okay. And then E, this is equilibrium, because here K dot is constant and also C dot is constant at 0. K dot is 0 and C dot is 0, which says that there's no change in physical capital per unit of human capital, and also no change in consumption per unit of human capital. So from this, the cool thing about these graphs, this is called a phase diagram. We can actually read off some dynamics of the model. Okay, so if we start at F, then we're gonna get, you know, this quadrant, recall that little c is increasing and little k is also increasing. Okay, so depending on where you start on these transition paths, let's see if you can see it out. My pad is not plugged in. All right, so depending on where you start here, you know, if you start on F, you're gonna get up to E, the equilibrium. So that's sort of the transition path from a starting point of capital. So this is K0, the starting point of capital, up to the equilibrium level. Now you can see that there's other places you could start here. So suppose that we, at K equals 0, we chose consumption at level C, or at level B, or at level A. Well, what's gonna happen is, ultimately, this consumption is going to diverge. Our consumption is gonna get higher and higher and higher, and our capital is gonna get lower and lower and lower. And in particular, actually, you could follow this line out. You keep drawing past this level to where you have negative capital. So this is actually the area where what we talked about is important. This this no Ponzi scheme condition. That's saying that we can't just raise our consumption forever by accumulating negative capital. Okay, so that's where you see it. Okay, and then down here, this level. So what happens is, if we start at D, then ultimately our capital is going to go to infinity, but our consumption is going to go to 0. So this one, we don't have a no Ponzi scheme condition to rule out. It's just that we know that it won't be optimal to do this, because ultimately consumption is falling to 0, and as consumption falls to 0, you know, the marginal utility is growing to infinity. So that's also just not, it's ruled out by optimality. So it turns out that the unique optimal choice of consumption given capital given our capital endowment is going to be the one that sort of puts us on a transition path up to equilibrium. Okay, these are all ruled out by the no Ponzi scheme condition, and these are ruled out by optimality. They're just not optimal. So we can actually draw the saddle path, which says that given any amount of capital that you're endowed with, you're going to choose the level of consumption that puts you right on the saddle path that's going to lead you into equilibrium. Right, I think this is the last slide. No, there's one more. So suppose that we're in equilibrium. Okay, so suppose we're sitting at this equilibrium, and then suddenly everyone becomes more patient. All right, suppose that happens. What's going to happen? Well, immediately consumption is going to drop. Why is consumption going to drop? Well, people have become more patient, right? They're willing to put off consumption more in order to have a higher consumption level later. And then how much is it going to drop? It's going to drop onto the new saddle path that leads us to a new equilibrium. If people are more patient, you won't be surprised that the new equilibrium is going to feature more capital in the long run, and also, in this case, more consumption. Although, you know, the golden rule level of consumption is like something like here. We didn't talk about it, but they talk about it in the textbook that actually in this model, consumption is always to the left of the golden rule level of consumption. Okay, so when you're in the Ramsey model, any additional sort of whatever induces us to save more is actually going to get us closer to the golden rule level of consumption in the long run. All right, that's all I have for this lecture. So for next lecture, we're going to talk about the overlapping generations model. So in this model, we've done this idea about households and having this, having people care about the next generation in a particular way. You know, there's a discounting rate. In the next chapter, we're going to think about generations that don't necessarily care about each other. So it's going to be one generation is going to live one period young and one period old, and then there's going to be an overlapping generation that is young when the first generation is old. And we're going to think about how that economy is going to work when people don't care about each other. Or I should say when people don't care about the next generation. And it's going to do some sort of interesting dynamics into the model. Okay, so I will stop there.